guided by my advisor. I really appreciate for his guidance because it's a milestone for me. Okay, let me first introduce what is the single constant multiplication. And this problem has the universe form under like a constant c dot multiplied by a variable x, and which is equal to another constant y. So here c is a fixed integer constant, and x, y are domain integer domain variables. And for this problem, it is a fundamental problem in digital signal processing, image processing, and communication circuits and hardware accelerators. Although we are doing in theory things pretty high level. And since c is fixed here, as we say that c is a fixed integer constant, so this multiplication can be implemented using additions or subtractions with bit shifts there. And if you're not familiar with the binary representation something, so we say that bit shifts are usually cheap or free because we don't, it doesn't incur some extra cost or overhead there, only shifts for bit for the representation bits. So encoding quality mainly depends on the reducing arithmetic operations there. Finding high quality decompositions is computationally challenging and NP hard, so that's why we are doing this research. And let me introduce more about this. Here we introduce three operators. First is S plus, that means a constant can be decomposed by two different constants, which is CL and CR. However, we shift CL, which is C left, right? The left operand. So we first shift the left operand and then we plus the right operand. And the second is S minus, that is the different, which is no longer making the additions, rather we use the subtractions. And the third one is minus shift. That is, we don't shift the left side while we shift the right hand side. So that is the three operations we have. And let me give you an example of the SCM problem. Here we say that there is constant, which is 55,450 there. We are going to decompose. So a general encoding may looks like in the left side there we have 6 steps or operations that reach the base case. That is the, as you can see, the x there, the coefficient is 1, right? That is the base case. Okay, while it takes 6 steps, however, we still have better encodings, that is listing the right-hand side. That is, we only take 4 steps there. So how can we find the better solutions? That is always difficult for us. And why we have to find a shorter path to reach the base case, as we said that there may be some, I don't know, maybe the different things like the circuits or image processings, they will have some power consumptions. So if we find a shorter path to decompose these constants, so the cost or maybe energy consumptions can be reduced. That is the motivation. And my project is based on a previous research that is guided by my advisor, that he proposed a dynamic programming with PyCat tabling to solve such a problem. And in the DP based approach, there is no machine learning applied there, only the traditional coding. In the dynamic programming side, it recursively explores the possible SCM decompositions, and it reuses the intermediate subprograms result using the tabling to solve such problem. And it is implemented in PyCat using the mode-directed tabling. It's a pretty powerful tool that helps us to get the solution. And for the DP method, it explores all the possible 3 operators during the decomposition, and it produces near optimal encodings. And the problem is that it still suffers from high time and memory cost for large constants because it explores all the possible 3 operators there. So at every decomposition step, DP must branch over multiple operators choices. This will lead to rapidly increasing search cost as the bit length grows. The bit length means the length for the binary representation of a specific constant. And this is the code sketch for the DP method. Here we have the base case that listed in the first, at the beginning, that SCM with a parenthesis beginning with 1 there. That is the base case. And after the base case, we divide the SCM into 3 cases that we may use the S plus, S minus, and the minus shift there. And the DP case will recursively explore these 3 operations until it may find a solution there. And the question here is that, can we, using the machine learning, to identify some good operator selection rules that reduce the DP research cost while preserving near optimal SCM encoding qualities? That means before we have 3 options there, but currently I may choosing the top 1 operators or maybe top 2 that may possible to lead the good solution. So we, instead of replacing the symbolic search, we are trying to using the machine learning to guide it. And we are going to learn which operator types are promising for a given decomposition state. And once we have such a good rules, or maybe, the suitable operators, we compile the learned predictions into the symbolic good rules. And we use the rules to prune the unpromising branches in dynamic programming. And here is the core idea of our architecture, that we using the GNN for prediction, and we convert the prediction into good operator rules, and then we're using the rules to help prune the search space, so that leads to the faster set encoding. Here is our architecture for the neurosymbolic framework. We first using the PyCat to pre-calculate some solutions and generate the SCM decomposition plans to gather all the solutions as our training set. And except for gathering the solutions, we have to convert each decomposition into a graph structure training dataset, as listed in the upper side. That is a JSON file structure there. And then we train a GNN to predict the operator types, and then which is the offline. And after we get the weights, we use the GNN. We using the model to help us to predict some new instances, and the instances output. The model will output the GNN confidence scores as listed in the downside there. There is a yellow framework that indicates the confidence score. So here we leverage the confidence score to identify the good rules. Once we have the good rules, and then we integrate it into the PyCat DP solver there. So that is overall ideas of this approach. And for our implementation details, we get the graph representations of the SCM decomposition in the following ways. We assume that each decomposition step can be represented as a directed graph. We have the vertex and the edges there. The nodes, we say the vertices is the target constant, and the intermediate constant there. For the edges, it represents dependency relationships between the parent constant and the operands. And each graph corresponds to partial decomposition history there. And the current constant to be decomposed is treated as the prediction node. So for example, if we have the 1759, the decomposition history can be gradually expand as first it will expand as the left hand side operand is 27, the right hand side is 31. Let me check whether we have a more, oh here, this is much more clear. The first step, we decompose it into the 27 and the 31 nodes, right? And in the second step, we recursively decompose the 27 or the 31. So that will lead all the decompositions to the base case. Okay, yeah. And let's see, this is a comparison encoding for the naive shift and add method with our SCM decomposition. For the naive shift and add method, that is, each time we only shift one time, right? So that makes this constant is only need to be represented using its own binary representations. And when we are using the SCM encodings there, so here we just need 3 steps, and each time we decompose it using 2 operands until we reach the base case 1. And this is the selected features that we used in our nodes and edges there. Actually, we designed up to 200 features there. It's a quite long time to thinking out of what features should be used. But it's okay, and we did it. And that is the overall process of the decomposition there. I've just explained that we are going to predict the operator types, and what we input the model is a graph representation that presents the partially decomposition, and this is the decomposition steps each time we use there. So why are we using GNN here is quite interesting. Me and my advisor has tried a lot of architectures like the normal CNN, LSDM, even like some random forest, something like that. But however, those architectures are not performing well. But only when we are trying the GNN, we find that, oh, the performance is pretty good. And after that, we realized that it is because GNN, it has some internal graph message passing mechanism here, and it is especially fit for this problem because for the SCM decomposition, it is relational and history dependent problem. So that makes GNN is perfect for that problem. And this is an overview for the message passing semantics. This formula is copied from the original paper, and what I want to demonstrate is the message passing process. Here we have the initial state, right? And at the node and edges, we have a sequence of blocks there. Like the green one, the yellow one, the blue one there. The message passing means that the node and the edges they are exchanging their informations. So as you can see, during this process, I mean the aggregation and update process there. So the node and the edges, for their feature vectors, they are exchanging their information. So making the colors becoming more and more colorful, mixed together there. Until we reach a state that, okay, the result is converged and the performance is no longer improved. And the trained GNN outputs some confidence scores, and where this is a representation for the confidence scores that O is an operator and the score is based on the C constant and the graph state. And we set some confidence rules there. There are 2 rules there. If the top operator is much more confident than the second best operator, that means we have a most promising operators there, and then we only taking the first one. However, if the two operators are close, like maybe 0.4 or 0.445, okay, there is only 5% gaps there. And then in this case, we take both operators to avoid overpooling. So in this case, we upgrade the original DP, which explore all three operator types, into using one or two recommended operators by the learning rules. Here is the updated code for our project. Here we import the good rules there. We compile it into another file, and then we import the file into the original DP encoder. Well, there's, of course, we modified the DP encoder there. Here, once we introduce the learn good rules, for the, if you can see in the downside, here we use the if else if, right? Which is a little bit different from the previous code that we explore all the three rules there. And in this case, we only explore one or two rules we will apply there. And in our experiment, we compare the baseline method, that is the direct shift and add encoding, which is represented as the original binary representations there. And also we compare the min k method, which is a mini-zinc based optimal min k model, and the DP method, that is our previous research. And the last one is our machine learning DP method there. That is the three methods we are comparing. And for the dataset, we construct our dataset using all the odd constants from 1 to 65 and 535. And we also generate 6,000 sample odd constants from bit length 17 to 32 there. So the training constant is up to 100,000 there. And for the test set, we generate 60,000 odd constants for the bit length from 16 to 32 there. Each has 1,000. And this is our result. So as we can see there, that DP gives the best addition count, but becomes slower for large constants there. For the time, it is not better. Actually, the baseline is always the best in time because it's only doing the shift things. It doesn't do any other logic things. And but the additions there, it is keep the highest because it is too simple, right? And for the DP method, as we can see, the time is not bad, and the additions keeps the lowest because as the adds is increasing from 4 to 7 only. However, the thing is that we want to trying to balance the time and encoding. So here machine learning makes that it runs in milliseconds even at the 32 bits. That means, okay, the time is acceptable. And for the additions, as we can see that machine learning achieves not bad additions, almost keep the same as the DP encoders, but it speed up a lot over the DP encoder as the time is only increasing from 0 to 0.0523 seconds there. That means, okay, the time is shortened strongly, and while this method is still keeping the same, almost the same quality as the DP encoder. And for the memory consumption and the branching performance, the machine learning DP method is pretty strong there. We didn't list the baseline and the min k method there because they are not using the same mechanism as the DP and machine learning DP, so they are not comparable. As we can see, there is an over 97 memory reduction from the machine learning DP to the original naive DP method. And the branching decreases from 60,000 to only no more than 1,000. That is because, as we mentioned a lot of times, that DP explores all the three possible ways, but the machine learning is determinedly only explore one or two operators there. That makes the branching decrease sharply. And the learned will significantly reshape and shrink this symbolic search tree. So as we say that this method, our method significantly accelerates the set encodings, right? And the learned good rules reduce the unnecessary operator branchings. When we compare all the results, machine learning thinks it's always doing not always doing the best, but it can have some better results balancing with the encoding time and quality time there. And the GNN here doesn't replace the symbolic solver, but just help us to do something. So our conclusion is that this work shows that the machine learning can effectively guide the symbolic set encoding by identifying good operator selection rules for this problem. And the overall framework is summarized as one component is the GNN-based learning, and then we integrate it into the PyCat-based dynamic programming there. But I think the most important thing is the PyCat's power, because GNN not only GNN, maybe we can using something else machine learning tools there, but the most important thing is the performance of the solver that can lead to a better solution and the performance. And what we have learned here is that we can learn some good rules to prune the unpromising branches and improve the problem's scalability. And this approach preserves the interpretability and the structure of symbolic search. And that is the end for my research. Thank you.
The audience have any questions?
Maybe you can comment on two things. First thing, in your slide 10 and 11, you're talking about the feature representation. Can you comment on why the number of bits is not part of your feature representation?
Here?
10 slide, yeah, like this, right? So 1759 can be decomposed to 27, shift multiply by 2 to some power, and that the n 2 to the nth power.
2 to nth power. Sorry, I didn't.
Well, basically, to understand correctly, 1759 basically decomposed to 27 left shift means equivalent to multiply by 2 raised to power the number of bits you shift.
Yeah.
Right? So if you left shift 3 bits means 27 plus multiply by 8. Supposedly either you plus 31 or minus 31 give you 1759.
Yeah.
Right. So why the number of bits shift is not part of your feature representation? Can you comment on that?
The number of shifts is not a part of my features, right?
That's right. Yeah. Well, why?
Because because actually what we design is we just trying to predict the left hand side and right hand side, and I trying to predict the shift amount there, but the performance is not good because they cannot capture the exact amount how many bits to shift. So in this case, we pass this task to the solver itself. Each time we only predict the left and the right, and for how many bits it is going to shift, and then the solver will do a brute force explore, like each time move one, each time move another one, like try one by one.
Thank you very much.
Yeah.
Maybe you can also comment on the second thing, right? So you tested on 32-bit integers, right? So they are 2 to the raised to the power of the 32nd number of integers. Following the dynamic programming, the the basic concept. If I have figured out the best decomposition for integer, I just store in the table. Next time, just look it up from the table.
Okay.
How about that?
Well, actually, getting the optimal solution takes a pretty long time. Yeah, currently we have the optimal model where it can solve only for 16 length bits, and some of them they can to get the optimal solution. It takes even 8 to 10 hours. So if for 32 bits you want to store the optimal solutions, the first thing is even you want to take the optimal solution, it will take maybe up to days to do that. So if you want to gathering all the 32 optimal solutions and store them in a table, okay, that is a good idea, but it takes a long time. And one important thing is that when you are doing the hardware circuit design, right, or doing the image processing, the constant you need is only limited. You don't need a 1 to 32 bits numbers. What you need is only a specific constants or several specific constants that may be vary in length. So in this case, you don't need to have it's better for you to have all the better solutions in a table. But the thing is, currently nobody wants to sacrifice so many times to get such a solution, because you have to balance the time and the cost and even other like utilities and the stuffs.
Thank you very much.
Thank you.
Memory consumption is a big issue. You want to store the code recipes for all these integers. Then you need I don't know how many terabytes you need.
2 to 32.
That's a lot.
By a factor. That's,
But I think the time is the big issue. Nobody wants to waste the time.
Yeah, the group in Australia.
4 terabytes
Yeah,
multiplied by the path.
Yeah, but the thing is, it's too big. For each one, you need to store a plan. The group at Monash University, they only do up to 2 to 16 integers.
If you store the 32-bit integer of that 2 to 32 is 4 terabytes.
It's
And
not
then we'll get
viable.
a pattern and
If
save it
then
to.
the rest of them, the decomposition
It's not viable.
It's not possible.
Well, at the end, you said that this is the end of my research. No, that's the start of your research. This is the end of your presentation.
Oh, it's the end of my presentation. I really want to thank my advisor taking me as his student. Yesterday, I took partially I completed partially my second exam. It's a milestone for me. I was thinking that it may take even longer because I'm just newcomer to this area. But he supported me during the first year. Pretty supportive. Well, I want to say I love you, but it seems not a problem. He is the most he is my favorite professor in this school. Well, I don't know what to say, but thank you. Thank you, Dr.